Hello everybody, and welcome back. This is Big Ideas, lesson 6.2 for Algebra 1. Today, we're going to be talking about radicals. But these vocab words look a little bit complicated for right now. Before we jump right into what a radical is and how you do math with them, I first want to go back to the absolute basics. So, let's say, for a moment, we have the following. Let's say we have 5 plus 10. So 5, and we add 10, we know that we would get 15. But what if I wanted to start at 15 and make my way back to 5? What if I wanted to go backwards? How can I do that? How can I go from 15 back to 5? Well, if I added 10 to get there, I can do the inverse to go back. I can subtract 10 to get back to 5. Let's do another one real quick. If I had 3 times 7, that equals 21. If I wanted to start from 21 and get back to 3, what would I need to do? Well, you may have noticed this one as well. I would need to divide 21 by 7 to get back to 3. Inverse operations, operations that cancel each other out and make zeros, or in this case, ones, their use is to go backwards. Instead of multiplying, dividing gets you back down to a smaller number. Adding will get you to a bigger one, subtracting will get you back down to a smaller one. The idea of inverses is that they undo each other, because there's nothing in math that you can do that can't be undone as well. But we do right now have something that we don't know how to undo. Let's say we take 2 to the third power. Well, we know that this is 2 times 2 times 2. 2 times 2 is 4, and that times 2 gives us our answer of 8. But we don't yet know a way to go backwards from 8 and get to 2. This is where radicals come into play. Before we talk about this complicated answer, because this is a cubed answer, let's talk about one that's even simpler down below. 4 squared. 4 squared, we know, is 16. If we wanted to get from 16 back to 4, an operation we might be used to doing is known as the square root. Now, many people have been exposed to the square root in the past. They're sort of familiar with it, maybe not completely well versed in it, but you know what it is. You may know that the square root symbol kind of goes around your bigger number, like this, and it gets you to the smaller one. So squaring something will make it bigger, square rooting something will make it smaller. It turns out that squaring and square rooting are inverses of each other. So for instance, if I go back up to this example with adding and subtracting, if I did 5 plus 10 minus 10, well, we actually don't need to do any math to solve this one. Because we know that plus 10 and minus 10 are inverse operations, you can cancel them out. We're just left with 5. It's the same thing with the square root symbol and the square symbol. If you were to take, let's say, 5 squared, and then take the square root of that, well, since the square root and square are inverse operations, there's no math that needs to be done. They'll cancel each other out, and you get 5. Don't believe me? Well, we can treat everything underneath this symbol, the square root symbol, which we'll later call a radical, we can treat it as if it's in parentheses. So we want to do 5 squared first. So what's 5 times 5? Well, that's 25. Now, to explain the square root. The square root of 25 asks you the following question. What number times itself makes 25? Well, we know 5 times 5 is 25. The square root of 25 is just 5 again. So, these two inverse operations would cancel each other out. 5 squared, and then you take the square root, that'll just give you 5. Square roots are a little bit weird, especially if you don't have much prior knowledge about them. That's why I have included in our Canvas page a small table to help you out. In the past, you may have been very familiar with these square roots over on this side of the table. These are the ones that we would expect at this point in your educational career that you have memorized or at least can calculate relatively quickly. For instance, the square root of 4 is 2, since 2 times 2 is 4. The square root of 9 is 3, since 3 times 3 is 9. The square root of 64 is 8, since 8 times 8 gives us right back to 64. The next column, we might expect that some folks will have memorized, but it's a little bit trickier to say. This one is one that we would try to aim to have memorized, hopefully by the end of Algebra 1. We'll do a lot of math with these ones, so don't worry, you'll get well acquainted with them. Everything beyond is sort of extra credit almost. If you're able to memorize these squares, it will be a fantastic aid to you in the coming years. If not, though, don't worry. These 3 columns are probably the most used. So, with all that being said, let's talk a little bit more about square roots. As of right now, you may be asking, is there a way to perfectly calculate square roots like the same way we do multiplication or division? Is there some way to instantly say what the square root of, let's say, 576 is without having to put much thought into it? The answer is, unfortunately, no. There is no easy way to calculate this out. However, what I can teach you in Algebra 1 is a method for being able to guess, check, and approximate your answers. Let me give you an example. Let's say we're trying to find the square root of something a little bit smaller, the square root of 169. In order to find the square root of 169, if you just know the answer, that's fine. In fact, that's fantastic. However, many people don't know this answer right off the gate. That being said, do we know some square roots that are close to it? For instance, you may recall that the square root of 144 is 12. And, well, 144 is pretty close to 169, right? Since 144 is less than 169, we also know that the square root of 144, which is 12, is less than whatever the square root of 169 is. You may also know, and this one's a little bit harder to really say if you know or not, that the square root of 196 is 14. And since 196 is bigger than 169, we know that the square root of 196 is bigger than the square root of 169. In other words, our number is going to be less than 14. It's going to be bigger than 12. Well, let's see if 13 is the correct answer. We want to just put it in right here, but how do we know it's not some weird decimal like 13.2 or 13.0001? We have to check to see if this answer is sufficient. So, let's try out 13 times 13 and see if we can get to 169. Many folks have not used this method of multiplication in a second, so I'll walk through it very briefly. You can skip this part if you are familiar. But 3 times 3 is 9. 3 times 1 is 3. Then since we go over to the tens digit, we're going to want to add a 0 to show that we're multiplying the tens digit. 1 times 3 is 3. 1 times 1 is 1. We then add these together. 130 plus 139 is 169. So we know that yes, 13 is the correct answer. 13 is the square root of 169. This method of guessing and checking works for any and all square roots. If you can find some square roots that are close to it, you can figure out if your answer should be higher or lower. Then it's a matter of guessing and checking. Let's say, for instance, that we knew the following. Let's say we knew that the square root of 400 is 20. Yet at the same time, we wanted to figure out what the square root of 484 is. Well, 400 is very close to 484. We know that square root of 400 is less than the square root of 484, so our answer has to be bigger than 20. Why not guess 21? Let's see what happens. 21 times 21. 1 times 1 is 1. 1 times 2 is 2. We add a 0 for the tens place. 2 times 1 is 2. 2 times 2 is 4. Uh-oh. We didn't quite meet our quota. 21 times 21 is 441. So it looks like 21 is not the correct answer. But this is useful because now we know the square root of 21. Or, sorry, the square of 21. Or the square root of 441. If 21 didn't work, let's try 22. This is going to be a fun one. 2 times 2 is 4. 2 times 2 is 4. We add a 0. 2 times 2 is 4. 2 times 2 is 4. That gives us 484, which is our answer. So we know our mystery square root is 22. This is incredibly useful as we go forward. However, I do have some news. This entire time, I have been secretly lying to you. In fact, not only have I been lying to you over on this sheet, and on this sheet, even this worksheet is lying to us here. Yeah, crazy, right? Because if we look at this number here, for instance, the square root of 36, 6 times 6 is not the only way to get 36. It's one answer, don't get me wrong. 6 times 6 is 36, so this is correct. But there is another number times itself that will give us 36. Pause the video here if you think you can figure out what it is. I'll give you a hint. 6 is very, very, very correct. Therefore, your number, the other way to multiply together to get 36, might have something to do with the number 6 as well. Pause the video and try and see if you can figure it out. Did you get it? If not, no worries, because this is going to be something that we'll get very used to in the next coming weeks. The other number times itself that'll give you 36 is negative 6. Negative 6 times negative 6. Well, we know 6 times 6 is 36. What's a negative times a negative? It's a positive. Negative 6 times negative 6 will also equal 36. So there are two answers to this. 6 and negative 6 are both answers to the square root of 36. Similarly, with this one, the square root of 49. 7 times 7 is 49, but isn't negative 7 times negative 7 also 49? And down here with 64, 8 times 8 is 64, so is negative 8 times negative 8, because two negatives will make a positive. For any square root, there are always two possible answers, a positive and a negative. We'll talk more about why this is in just a second. But keep this in mind, because we will have to develop a rule for it later. That said, I think we've finally done enough prep work to jump into the notes. So, in our notes here, we start off with this phrase, the nth root of a. This is sort of interesting, because we've talked about square roots before, but never nth roots. If we go back to the sheet here, I kind of previewed this idea. 4 squared is just 4 times 4. But your exponent could always be bigger than the square. What if it was cubed? For instance, 2 cubed is 2 times 2 times 2. So if we wanted to get back from 8 back down to 2, we would need to figure out a way to figure out what number is multiplied 3 times to this 8. So a square root symbol won't do anymore. The square root symbol means what number multiplied twice will equal the number inside. If we're looking to see what number times itself 3 times will equal 8, we add a little tiny 3 next to it. We call this the cube root. Here is the rule. The nth root of a is always written like this. A is the number we're trying to find the root of. Your symbol here indicates that we're trying to find the root. And whatever number we put in place of this little tiny n that floats above the little tail of this symbol, that tells us how many times our mystery number has to multiply itself to get to a. The phrase, the nth root of a, means the following. What number times itself n times equals a? What number times itself n times equals a? Let me give you another example. Let's say we had this problem. We have 27 underneath. That's our value of a. And 3 is our value kind of hovering above the tail here. That's n. So this is asking us what number times itself 3 times equals 27. This is a thinking problem. Root problems are all thinking problems, where you really have to go through and ask yourself, what number could I multiply by itself 3 times to make 27? It may require some guessing and checking as well. For instance, let's say I guessed out of the blue the number was 5. 5 times 5 times 5. Well, what's 5 times 5? Well, that can simplify to 25. So what we're really asking is, what's 25 times 5? That's a pretty big number. That's 125. So we know, hey, the cube root of 27 is not 125. Can you figure out what number times itself 3 times will equal 27? 5 is too big. It gets you all the way up to 125. You may have already suspected the number 3. Let's try 3 out. 3 times 3 times 3. Well, 3 times 3 is 9. And 9 times 3 is 27. So yes, the cube root of 27 is 3. We could do another problem like this just for practice. Let's say I wanted to try and figure out, let's do the 4th root of 81. Now we're getting into some weird stuff. First, ask yourself, what is this question asking you? Well, it's asking you, what number times itself 4 times will equal 81? Give yourself a moment to try this one out. Pause the video here and see if you can figure out what number times itself 4 times will equal 81. Hopefully you've had a chance to pause the video and try this one out. The correct answer here is 3 again. Kind of gave you a tricky one here. But you may have noticed a little bit of a pattern. Since 3 times 3 times 3 we already talked about is 27, this is really asking us, well, 3 times 3 times 3 is 27. What's that times 3? In other words, 27 times 3 is 81. These are the type of problems we'll be encountering. Now, a little bit about what we're doing here. The symbol that's being used right here, we actually have a name for it, and it's called a radical symbol. And the number underneath, A, is called the radicand. Fun fact about the word radical, can you think of a food that starts with the letters R-A-D-I? If you said radish, there's a reason for that. Radish and radical actually come from the same word. They mean the same thing in Latin. The Latin word radix means root. A radish is a root. And what we're talking about are roots. So, they mean the same thing. Radical and radish both mean root. Kind of an interesting little tidbit there. The index of a radical is another piece of this. We have our radicand is A. We have our radical symbol, which is the square root symbol. Our index is n. N is what we call the index. And n is always going to float right over the left-hand side of our radical. The index tells you how many times you're going to multiply our mystery number by to get to A. So it tells you how many times our number is multiplied. On the other hand, there is a little bit of a trick with this. Think about if I gave you the following root. Let's say I wanted to find the 8th root of 1024. That's a big number underneath the symbol. But it makes sense that's such a big number too, right? We have to multiply a number by itself 8 times to get to 1024. It's kind of crazy, isn't it? Well, there is a rule that can help us figure out what this answer is. The bigger the index, the smaller your answer. Bigger index equals smaller number. Can we take a guess what the 8th root of 1024 is? Well, for this particular problem, the 8th root of 1024 ends up being a decimal. It ends up being around 2.3. gave you a little bit of a tricky one here. This one doesn't actually give you a regular number, and that was my fault. But it ends up being around like 2.3. We'll approximate that. That's a very small number to get to such a very big number. Let me see if I can give you one that actually ends up with a real answer. Let's say I wanted to find the 7th root of 2,187. Well, I'll tell you the answer to this one right now. It's 3. 3 times itself 7 times will get you there. 3 times 3 times 3 times 3 times 3 times 3 times 3. So the bigger the index, 7, the smaller your answer has to be. This is very helpful when we have to solve problems involving huge indices. However, this also does bring up a little bit of a question. Let's go back to another one of our previous problems, the cube root of 27. We said that the answer to this one is 3. But the question is, could our answer also be negative 3? Could our answer be negative 3 as well? Well, it worked for all the squares. Let's see how it works for the cubes. So the cube root of 27, again, is just asking what number times itself 3 times will equal 27. If we tried out negative 3, multiplying itself 3 times, what's negative 3 times negative 3? A negative times a negative is a positive, so that becomes positive 9. And 9 times negative 3 is, negative 27, not positive 27. So it turns out negative 3 is not an answer to this. What's going on? Well, remember how we talked about square roots having multiple answers? For instance, the reason why negative 6 works is because a negative times a negative is a positive. If we multiply that positive by another negative, like we did here, we multiplied 3 negatives together, your answer is going to be negative again. So it won't work. What about the 4th root of 81? We already talked about that one too. We said the answer to that one was also 3. Could this one also be negative 3? Well, let's try it out. This is looking for 4 numbers multiplied together. If those numbers are negative 3, well, we already talked about negative 3 times negative 3 making positive 9. So this is 9 times negative 3 times negative 3. We already talked about 9 times negative 3 giving us negative 27. So this is negative 27 times negative 3. And what is negative 27 times negative 3? It gives you positive 81. So yes, 3 and negative 3 are both answers to the 4th root of 81. It turns out there is a rule that tells us whether or not we'll have one answer or 2 answers. If your index, n, is odd, you will only have one answer. If your index is even, you will have 2 answers. However, we did talk about this rule earlier on, but in Algebra 1, we will not be discussing the answer to something like the square root of negative 64. We know the square root of 64 is 8, but the square root of negative 64, there's no number, no real number at least, that can be multiplied by itself to get a negative 64. 8 times 8 is 64. Negative 8 times negative 8 is still positive 64. We say that if our index is even and we have a negative number for our radicand, there's no real answer. We can't do it. So what I want you to do now is this. let's get a little bit of practice in. I want you to try the following problems. Actually, I'll walk you through number 1 first. Problem number 1 asks us to find the roots, given that n is 2 and a is 64. What this question wants us to do is it wants us to put this in radical form. The nth root of a. Well, n is 2, so that tells us our little number is going to be 2, and a is 64. We know the square root of 64 is 8. So 8 would be the answer to number 1. But, is there another answer? You always have to ask, is there another answer? Since our index n is even, we know there has to be. And that answer is negative 8. It's the negative version of our previous answer. What I want you to do is I want you to try out these problems, these 5 here. Don't worry, I'm not there next to you. I'm not going to be looking over your shoulder. But it is helpful for us to get this practice in and try it out for yourself. Puzzle these through. And remember, the bigger your index, the smaller your answer will have to be. Try these out on your own. Pause the video, and we'll come back and show the answers. How'd you do? We get 3 for number 2, 4 and negative 4 for 3, 3 for 4, 2 and negative 2 for number 5, 10 and negative 10 for number 6. Instead of writing it out as 2 separate answers, we can write it in a different format as well. I wanted to show you this real briefly. Instead of writing positive 4 and negative 4, you can just write it like this. Plus or minus 4. This symbol here means positive 4 or negative 4. Both answers are put into one place. So if you wanted to, you could rewrite all of your answers as plus or minus their respective versions. Keep in mind, it won't work when there's only one answer. If your only answer is 3, it wouldn't make sense to put plus or minus 3. You would just write it equals 3. All right. There is one more thing I want to talk about, and this is sort of a big thing. Unfortunately, this is also something that is very tough to discuss. So let me do it on a separate sheet of paper for you. So let's say I gave you the following qualm or quandary. I said, hey, I've got this number, 2/3, and I want to rewrite it as 2 numbers being multiplied together. Well, how would we do this? We would have to think of it as this. 2/3 is the same as 2 1/3. It's the same as if you had 1/3 2 times. So we could write 2/3 as 1/3 times 2. How could we write out 5/7? Well, 5/7, that's 5 versions of 1/7. 5 times 1/7, or 1/7 times 5. You can always split up fractions by multiplying the numerator times a fractional denominator. We have a little bit of an issue. We know, for instance, that 2 cubed equals 8. That's perfectly reasonable. We understand that. However, what if I gave you something a little more interesting? What if I gave you something like this? 8 raised to the 1/3 power. Mr. Strager, what are you talking about? We've never done anything like this before. You'd be right. Here's the secret. Fractional exponents are the same as roots. 8 to the 1/3 power is the same as the third root or cube root of 8. Why is this? It all comes down to our inverses. We know that 2 cubed is 8. But let's say I wanted to use an inverse operation here. I wanted to get from 2, cube it, and then do something else to make it back to 2. We have a rule that we can use, the power of a power property. If we had some exponent to multiply the top by, 3 times that, we could get back to 2 to the first. But that brings up another question. 3 times what will equal 1? 3 times 1/3 equals 1. In other words, 2 cubed to the 1/3 power, we can rewrite as 2 to the 3 times 1/3 power, which is just 2 to the first, which is just 2. We've done it. The inverse of cubing something is taking it to the 1/3 power. But we also talked about how the inverse of cubing something is taking the cube root. These two mean the same thing. Cube rooting something is the same as taking it to the 1/3 power. This can be extremely, extremely useful because we don't have to worry about all this clunky sort of terminology. We don't need to worry about our roots clogging up our math. We can just write it as another exponent. So if I asked you, for instance, all the way down here, what we thought of this problem. 11, which says 729 to the 1/6 power. This is just asking us, hey, what is the 6th root of 729? Try this one on for size. This is, again, going to be a little bit of a tough one, but the rule that helps us is the bigger the index, the smaller your answer has to be. Did you get it? The correct answer to this is 3. But we have an even index, so we write it as positive and negative 3, plus or minus 3. This is where the last part of the notes come in, up here. Rational exponents, which you might hear me call fractional exponents. Rational numbers are just numbers that can be fractions. Here's the rule. If you have some number raised to a fractional exponent, you know that the denominator of that fraction is going to become your root symbol. The problem is, what if we had a numerator as well? Let's say we had the problem 27 raised to the 2/3 power. Well, if it was 1/3, we know we could rewrite it as the cube root of 27. But we don't have it raised to the 1/3 power. It's raised to the 2/3 power. It doesn't mean we go home and give up. There was a reason, a method to my madness before with asking you questions like these. How can I write 2/3 as two numbers being multiplied together? We said we could write it as 1/3 times 2. So let's rewrite it as 27 to the 1/3 times 2. Hang on a second. We know that exponents being multiplied together, that's the same as our power of a power property. That'd be the same as if we wrote it like this. 27 to the 1/3 power squared. And 27 to the 1/3 power, we can rewrite as radical. In radical form, 27 to the 1/3 power is the cube root of 27, and this is being squared. Well, what's the cube root of 27? The cube root of 27, we've discussed many times now, is 3. So this is asking, what's 3 squared? Your answer is 9. There is another way to do this problem too, you may have wondered. Instead of writing it as 27 to the 1/3 times 2, could we write it as 27 to the second times 1/3? Yes, we can. Although this particular form for this particular problem may not be as helpful to us. Let me show you. What this is saying is 27 squared to the 1/3 power, which we can rewrite as the cube root of 27 squared. 27 squared is already a little bit of a big number. It's kind of a big ask here. 27 squared is 729. So what this is really asking you is, what's the cube root of 729? This is a tough problem. The answer does end up equaling 9, but you see that it's probably a lot harder to do than making your number smaller first and then squaring it. This type of problem is very interesting because there are 2 ways of doing it, and you have to kind of fiddle with it to figure out which way is best. Do you root your problem first and then square it? Or do you square your problem first and then root it? Let me give you an example of a problem that might make this a little bit more reasonable to see the difference. Let's say I gave you the following problem. I wanted you to tell me what 5 to the 4/2 power is. Well, we could rewrite this as 5 to the 1/2 times 4, which we can write as, if you wanted to skip a little bit of a step here, the square root of 5 to the 4th power. Oh, shoot. I don't know what the square root of 5 is. Throws a little bit of a monkey wrench into things, right? If I don't know the square root of 5, I can't take it to the 4th power. That's why you can always do it the other way around. Let's say we have 5 to the 4th times 1/2 power. This would just be the square root of 5 to the 4th. Well, 5 to the 4th ends up giving us 5 times 5 times 5 times 5, 625. And the square root of 625 is 25. Of course, this problem is a lot easier when you consider that 4 over 2 can be rewritten as just 2. 4 divided by 2 is 2. So if you can simplify your fractions, it makes it a heck of a lot easier. But I just wanted to demonstrate that you can do it either way. It depends on what's easier for you. With that being said, everybody, that concludes the end of our 6.2 notes. I hope you have a fantastic rest of your day, and as always, I will catch you next time.